Welcome to Calculus. Today we will investigate using calculus to graph functions. We'll take a look at one example. Our example here is a quadratic function, y equals x squared divided by 2 minus 3x plus 9 divided by 2. And we want to use calculus to graph this quadratic, this parabola. And really what we're looking at with this task of graphing a function using calculus is putting together all of the analytical considerations that we've been working on. So we've got a checklist. We want to start by finding domain, x-intercept, and y-intercept. We want to find the asymptotes of the function. We want to find critical numbers, intervals on which the function increases or decreases, local maximum or minimum values by first or second derivative test, and then inflection points by test for concavity. And then we want to graph the function. Let's start with the very first task there. We want to start off just by deciding what is the domain of this function. And really when we're looking for domain, what we're kind of on the lookout for are there any restrictions in the equation of the function that would not allow us to graph the function at that x value. And so for a quadratic, we don't have any restrictions. Normally we'd be looking for some value that would make a denominator undefined. But with a quadratic, we don't have that feature. So we're going to say that our domain is all real numbers. And then we want to switch over to say, okay, what are the x-intercepts? So to find x-intercepts, our task really is to take that original function and say, where does it equal 0? Since the y value will equal 0 when a function crosses the x-axis, that's our strategy. So I'm going to take the original function x squared over 2 minus 3x plus 9 over 2 and set it equal to 0. And then we want to solve. So this is a quadratic. I want to get rid of this denominator 2. So I'm going to multiply each term by 2. I'll put the 2 there, but it's going to multiply to each term. So then what we'll have is 2x squared divided by 2, which is just x squared, minus 6x plus 9 divided by 2 times 2 is 9. And then 0 times 2 is just 0. So that lets us, in this case, factor. This is going to be x minus 3 times x minus 3. Negative 3 times negative 3 equals positive 9. Negative 3 plus negative 3 equals negative 6. And that's going to give us two solutions. So from the first binomial, x minus 3 equals 0, we'll set up the second solution's equation, but once I see that they're the same, we really just have one solution. So I'll add 3 to both sides, and we get x equals 3. So we see that this function has only one intercept, x-intercept, at 3. Last task for intercepts is to find the y-intercept. Now for the y-intercept, the strategy is to say, okay, that's where the function has an x value of 0. We want to find the y value. So what we'll do here is, instead of setting the equation equal to 0 and solving, we're going to plug in 0. So this is 0 squared over 2. Anytime I see x, I'm putting 0 minus 3 times 0 plus 9 over 2. And this solves very quickly. This equals 9 over 2. So we'll formalize at this point. Our x-intercept from this x equals 3 is going to be 3, 0. Our y-intercept is going to be 0, 9 over 2, or 0, 4.5. And that completes that first task. We found domain, x-intercept, and y-intercept. For the asymptotes, in that case, we're really looking for something that's happening in a denominator. Now, since this function has no denominator, we can assume it's got no asymptotes. The other case where we might have an asymptote is a exponential function or a logarithmic function. But again, this is a polynomial function, so we'll just make the observation there's no asymptotes. Our next task is to find the critical numbers. And we're told here, set the derivative equal to 0. So the idea is we're looking for max or min values on the function. And the rationale behind setting the derivative equal to 0 is at a maximum or a minimum, what we would say is the function has a tangent line with a slope of 0 at that point. So that's the rationale for setting the derivative equal to 0. So let's find the critical numbers for this quadratic function. So again, I'm going to take the derivative. Derivative of y here is going to be 2 over 2 x to the first minus 3, which is just going to be x minus 3. So that's a very simple linear equation. We're just going to set it equal to 0 and then solve by adding 3 over. And that immediately gives us this critical number, just one of them, but it is given it to us, of x equals 3. Now we've already seen in the function that the point that has the x value 3 is 3, 0. So what we're seeing here is that our x-intercept is corresponding to our critical number. We'll decide in a moment whether that's a local maximum or a minimum. But before we do that, we want to now say, where are the intervals on which the function increases or decreases? So we're going to use what we found here with the critical number. I'll just put a dashed line and then increase, decrease. So remember, for increase, decrease, what we're looking for is what's the value of the derivative on either side of the critical number, in this case 3. So I'll put a 2 and I'll put a 4. And we're looking for the value of the derivative as an output. So this is the function x minus 3. So we'll go 2 minus 3, that's negative 1. So the output for the derivative at 2 is negative. So in that case, the function's decreasing on the interval from negative infinity up to 3. 3 we already saw, if I plug it in, is 0. 3 minus 3 is 0. And then 4, if I plug it in, 4 minus 3 is 1. That's a positive sign, so that's indicating the function's increasing to the right of that critical value from 3 to infinity. All right. At that point, we do want to now decide if our critical number that we found is either a max or a min. So we're going to run let's run the the first derivative test, since we've already really come up with values that'll give us information. And actually, we don't need to calculate a whole lot, because what we're seeing is that we're going from a negative sign to a positive sign at x equals 3. So if I'm making that change from a decreasing to an increasing, that indicates that this is going to be a relative minimum. The function's y value is decreasing as x moves to the right, and then it increases as x continues to the right. So that's going to be a minimum value. And then our last test here that we want to run before we graph the function is the concavity test, which does require us to take the second derivative. So we'll do the test for concavity. So I'm going to take the second derivative. If my first derivative was x minus 3, our second derivative is just going to be 1. And that's a constant function, which indicates to me that this is always going to be concave up. It's a positive value. So there's no change in concavity throughout the function's domain, which means that there will be no inflection points. To have an inflection point, we would need to change concavity from concave up to down, or vice versa, concave down to concave up. And at that point, we have all this information that will allow us to graph this function. So I'm going to start off just by plotting the x-intercept. So that's +3. That's also my minimum value. So that's going to be the vertex of this quadratic. And then I know that it's got a y-intercept of 4.5. And that's 3 to the left. So based on the symmetry of a quadratic, I could go 3 to the right and go up 4.5 as well. And then what we saw from our increase decrease is on the left side, the function is decreasing. And then on the right side of that critical number at 3, which is our minimum value, the function's increasing. And we can check for concavity. The way we have it drawn is it's concave up the whole way, which corresponds to our test for concavity, which said there would be no change. It would be concave up the whole way. And that completes this example about using calculus to graph a function. Thanks for joining for this example. See you soon.